Okay, so we're going to talk now about the electronic structure of atoms. Chapter 4, Section 6 is about electron energy levels, and there's a lot here. So I'm going to start out with talking about how we measure energy in atomic systems, okay? And we're going to talk, first of all, about electromagnetic radiation, right? So we experience electromagnetic radiation in different forms, such as light, which is the colors of the rainbows, or X-rays, or gamma rays, or hopefully not gamma rays, those are pretty high energy, radio waves and microwaves and so on. So these are all examples of electromagnetic radiation. Electromagnetic, I have a hard time saying this word, so I'm going to try to push through. Electromagnetic radiation consists of energy particles that move as waves of energy. They are both particles and waves. Doesn't make any sense. It's something that has befuddled scientists for years and years, but it's I think I find to think about it like this. They are particles that move as if they're waves of energy, right? And they're massless, so they're little particles, but they have no mass at all. The distance between the peaks of the waves in the trajectory of the energy particles is called the wavelength, right? And high energy radiation has shorter wavelengths. Low energy radiation has longer wavelengths, okay? So here's sort of a graphic, which every chemistry textbook has, that sort of gives you an idea. It's a little bit busy, but I want you to take a minute and look at it. We have the shorter energy, the shorter wavelength. Can you see a wave right here? So the shorter the wavelength, the more energy the electromagnetic radiation has. So you see infrared right here. It has a wavelength is the top number here. This has a wavelength of about 1 meter. You see that in wavelength in meters? There's 1 meter right there. If you have a in EM radiation that has a wavelength of 1 meter, it's a microwave. Can you see that? And if it has a wavelength of a kilometer, it's radio waves. Okay? Or kilometers right there, sorry. If you have a wavelength of kilometers, it's radio waves, right? And if it's 100 meters, it's a radio wave. 10 meters, you can see we're getting into the microwave region, okay? If it has a wavelength of 1/10 of a meter, it's a microwave. If it's 1/100th of a meter, it's a microwave. Well, again, we're sort of getting into the range here. If it's 1/1,000,000th of a meter, that's what we call micrometer, okay, or a micrometer. If it's 1 micrometer, it's infrared radiation, okay? And now if it's, excuse me, 1/10,000,000th of a meter, then all of a sudden our eye can detect it and it looks like light to us, okay? And of course, shorter, and if you get it too short, your eye can no longer detect it, and it's ultraviolet, and it's really small wavelength. Now this is where we get into high energy radiation, is ultraviolet, and higher energy yet is X-rays, and this stuff is so high, such high energy that it can break apart molecules in your body. Okay, so which makes it please pardon me, it makes it dangerous. All right, now the frequency is higher and higher and higher as the wavelength gets lower and lower and lower. Right, that's not necessarily going to be too important to us, but it's important to appreciate what this graphic looks like. Okay, so wavelength light or EM radiation goes pretty fast, right? Speed of light, and so these two correspond to each other reciprocally. So I don't think I'm going to say anything else about that. The visible light portion here is sort of stretched out. You can see that. Visible light comes from the sun and other places, and it's got a wavelength of 700 nanometers to 400 nanometers, where 700 nanometers is red and 400 nanometers is blue or violet. Okay? I don't think I want to say anything else about that. And then finally, it turns out that if you take any particular element and you excite the electrons, as the electrons fall back down into their ground state, they will let off energy. Okay? And if you take, for example, barium, if barium is excited, in this case by a flame, if it's excited, the light that comes out of it as the electrons go back down to their ground state, the light that comes out of it can be split up into its, with a prism, can be split up into its component parts, and it turns out That the barium spectrum, that is how the electrons relax in there to their ground state, has these particular wavelengths in them, right? Can you see blue, a little more blue, okay? Yellow and red, okay? That's the barium spectrum of light. We'll say more about that. Not a whole lot more, but a little bit more in future discussions.